All right, we're going to take some notes on magnetic force. So let's start with the term magnetism. So magnetism is a physical phenomenon produced by the motion of electric charge, resulting in attractive and repulsive forces between objects. So that's the key part there. Attractive and repulsive forces between objects due to electric charge. All right, so the word magnetism came from this province in Greece called Magnesia, and they discovered there this lodestone about 2,000 years ago that had these really weird properties. Like they noticed that things that were metal were sticking to these stones, and so that's where the term magnetism came from. So a magnet is a piece of material that is able to attract certain metals. So not all metals are magnetic. So which of the metals below are magnetic metals? So see if you can identify which ones are magnetic. And this was in the Bill Nye previously. All right, so only iron, nickel, and cobalt are magnetic. Okay, the rest of the metals that we see here are not. And here's what they look like. So we have iron, cobalt, and nickel. Now, a little background, 16th century William Gilbert was the one who discovered that every magnet has two poles, a north and a south. And the like poles are going to repel. So south and south will repel, north and north will repel, and unlike poles will attract. Okay, so opposites attract. So with that information, we should be able to kind of fill out this table. So if we had north and north, would that attract or repel? Okay, you should have said repel because they're the same. North and south, attract or repel? Okay, those would attract. They're opposites. South and south, attract or repel? Okay, those are going to repel because they're the same. And south and north? Okay, attract because they're opposites. So you might want to record some of this on your notes if you like. I don't know if there's really a place, a question that went directly with this. Okay, so what is a magnetic field? So the region around a magnet where it has a magnetic effect is called its magnetic field. When a magnetic material is placed in a magnetic field, it will experience a force. So we can see this force if we take these little iron filings, so these tiny little pieces of iron, and we put them near a magnet, you will actually be able to see what that force looks like, kind of this circular movement of that magnetic force. And we can see the direction of the forces in that region. Okay, so what is the shape and direction of the lines of force in a magnetic field around a bar magnet? So we're going to look at a north and south. Okay, so we know that north and south attract. So this is what the magnetic field would look like around this magnet. Okay, so we have the strongest field is going to be at the poles. Okay, the weakest field is going to be further away from the poles. Okay, so where is the magnetic field the strongest? At the poles. Okay, here's another image showing iron filings placed near a bar magnet, and you can see that they align themselves on the field. You can see this whole field and some sticking. Okay, what do you notice about the pattern of the lines of force in the region between these two north poles? Okay, so you should notice that there is no magnetic filings really between these. And why is that? Well, we know that they're repelling. Okay, now if we put north and south together though, we see that, yes, the pattern does show that it continues and we get these circular patterns of attraction. I'm not going to have us explore this simulation, but you can see here, try and identify which one would be attracting and which one would be repelling forces in A and B. Which one is which? All right, so you should see that A is attracting and B is trying to repel. There's almost like a wall right there. All right, so another fun fact, cut magnets, if you break a dipole magnet in two, you get two smaller dipole magnets, not an isolated north or south pole. So no matter how many times I break this magnet up, there's always going to be a north and a south pole. All right, so now we're going to talk about magnetic domains. So magnetism is due to the movement of electrons within atoms of matter. So before magnetation, we can see that electrons are kind of flowing in all different directions, okay? And when we look at the domain after magnetation, we see that all of the electrons are flowing in the same direction. They're flowing in a line. So a region in which many atoms have their magnetic fields aligned is called a magnetic domain. All right, a ferromagnet or ferromagnetic is a material that can be magnetized because it contains magnetic domains. So we see our unmagnetized version here, okay? They're randomly aligned, and we see our magnetized version here. We put this item in a magnetic field, and now all of the electrons are aligned. All right, so this is pretty cool, the world's most powerful magnets. The two biggest magnets reside at Los Alamos National Laboratory in New Mexico and Florida State University. The magnets can reach 145 Tesla, respectively. By comparison, junkyard magnets, the one that lift cars, are about 2 Tesla. Okay, so this is a super, super strong magnet. The Los Alamos magnet is designed to generate fields that last only a few seconds, while the Florida State can maintain its fields for as long as the power is on. All right, so this is another little fun fact. Did you know the cow magnet? So there's a cow magnet, and these super strong magnets earn their name from helping cows from developing the dreaded hardware disease. So while grazing, cows would eat everything from grass and dirt to nails, staples, bits of wire. This wire would tend to lodge in their honeycombed walls of the reticulum, threatening the surrounding vital organs and causing irritation and inflammation known as hardware disease. The cow would lose their appetite and decrease their milk output if they were dairy cows, or their ability to gain weight if they were feeder stock. Cow magnets help prevent this disease by attracting stray metal from the folds and crevices of the rumen and reticulum. So a rancher or dairy farmer feeds a magnet to each calf at branding time, and the magnet settles in the rumen or reticulum and remains there for the life of the animal, and it'll attract any kind of foreign bits of metal that might get into their system. Fun fact. All right, here's a quick video of magnets as brakes. I hope the sound you'll be able to hear.
Now, magnets are everywhere. They're in computers, televisions, hi-fis, fans, washing machines, stereo equipment, tape players, absolutely everywhere, right down to the humble fridge magnet. And they vary in scale enormously, from the microscopic right up to the planetary. That's right, folks, we're sitting on the biggest magnet of all, the Earth itself.
So what is a magnet? Well, a magnet is defined as any object that attracts iron and produces an external magnetic field. And as you probably learned at school, the regions at the end of a magnet, where the external magnetic fields are strongest, are called the poles. And every magnet has 2, one north and one south. And the first law of magnetism is that opposite poles attract while the same poles repel.
And because the Earth is one big magnet, if you suspend a simple bar magnet within the Earth's magnetic field, it will naturally orientate itself north to south. And this is exactly how a compass works. It's been discovered.
All right, I'm going to pause this. I'll show this to you guys for a warm-up, just to save time. And we'll save that one too. Okay, so in summary, when 2 like poles are put together, they repel. When 2 unlike poles are put together, they attract. And scattering iron filings around a bar magnet makes it possible to see the lines of force of the magnetic field. All right, so let's look at the Earth as a magnet. So moving molten iron in Earth's outer core causes most of Earth's magnetic field. Okay, so we know that our core is made of iron and nickel. And that's what creates this magnetic field. Okay, we have convecting iron and nickel in our inner and outer core. Okay, a compass needle in the earth, any magnet will twist because of the forces between its poles and those of the earth. So we're able to use a compass because of Earth's magnetic field. Okay, the magnetosphere is the area surrounding Earth affected by Earth's magnetic field. So you've learned previously that we have different spheres, hydrosphere, atmosphere. Well, there's also a magnetosphere. All right, so magnetic field poles are not aligned with geographic poles. They wander and flip every 500,000 years between flips. Well, every 500,000 years it'll flip, and it takes about 10,000 years to completely flip. So our poles, we have recorded, if you remember Seafloor spreading, that magnetic field reversal over, obviously hundreds of thousands of years. Okay, so this is showing the magnetic field between reversals and during reversal. So it looks kind of crazy. All right, and there's a short video, but I will save that as well to show you in class. We are done with the notes.